Hello students, welcome. Today lesson 7, Form 4, Topic 4. We are going to do mixed concept on the uses of the standard electrode potentials. Previously, we were dealing with the uses of the standard electrode potentials, but today we want to combine all the uses of the standard electrode potentials in one question. Let's go to examples. Example 1. We are told study the standard electrode potentials for the half cells given below and answer the questions that follow. And in bracket we are told the letters do not represent the actual symbols of the elements. So these are the half ionic equations with the standard electrode potential values. So in part A, we are told identify the strongest oxidizing agent. Full stop. Give a reason for your answer. So when you're asked to look for the strongest oxidizing agent, we are supposed to look the one that's having the most positive electrode potential value. These are the standard electrode potential values. So you have to check the one that's having the most positive or the highest positive value. So here it is this one. So that means the substance or the species or the element that we're supposed to select there is G. So remember we're told give a reason. So we can say it has the most positive electrode potential value. Electrode potential value. That will be the reason. So we proceed to part B. We are told select the strongest reducing agent. Then we are told give a reason for your answer. So if the strongest oxidizing agent, it is the one that's the most positive. So that means the strongest reducing agent will be the one that's the most negative. So if we check, it is this one, the one that's having the most negative, negative 2.92 volts. So that means the species or the substance or the element is N. So we're going to say N, full stop. So what will be the reason? The reason will be the opposite of what we have said in part A. So you say it has the most negative electrode potential value. Electrode potential value. That will be our reason. So we proceed to part C. So in part C, we are told select or which two half cells will produce the highest potential difference when combined. So we are told which two half cells. And check here, we have several half cells. So the ones that when connected or when combined produces the highest potential difference will be the one that's the most positive and the one that's the most negative. So we're told give or which two half cells. So we have to take the half cell with the most negative and the half cell with the most positive. So our answer will be, we can talk about the one with the most positive, which is G plus. We are having aqueous plus electron. We are going to get G, which is solid. So the other one was N plus aqueous plus electron. Then we are going to get N solid. We are told which two half cells will produce the highest potential difference when combined. So for you to know the two half cells that produces the highest potential difference, you have to know the half cell with the most positive electrode potential value and the half cell with the most negative electrode potential value. So if we check the half cells given, we are having this half ionic equation with the most positive electrode value, and this one is the half cell with the most negative electrode potential value. So during the exam, you can be told to give a reason. When you are given a reason, we can say the one with G, as you have seen, was the element with the most positive electrode potential value, and the one for N was the element or the species with the most negative electrode potential value. So when they are combined, they produce the highest potential difference. So in part D of the question, we are told draw an electrochemical cell for the cell above and show on the diagram full of electrons. So first of all, let us check the cell, the half cells we have selected. If we check, we have selected G and also that side of N. And if you check the half ionic equations given, N was the reducing agent because it's the most negative, and remember G, it is the oxidizing agent because it's the most positive. Okay, so when we are drawing the electrochemical cell, we are supposed to have first of all two beakers. These are the two beakers. Then in those two beakers, we are going to put solutions of the most reducing agent and the most oxidizing agent. That means the most negative will be placed on the left hand side of the electrochemical cell, and the oxidizing agent is placed on the right hand side of the electrochemical cell. So those solutions are dipped into electrodes of the metal. N rod or N electrode, we can write it or we can label it there, that electrode, and here it is the side for the oxidizing agent, so we are supposed to put the rod of that oxidizing agent. That's G electrode or G rod. Then remember we are told show on the diagram full of electrons. So electrons follow from the reducing agent to the oxidizing agent, or the side where oxidations occur to the side where reductions occur. Remember we said oxidation is loss of electrons. So the substance that undergo oxidation is the reducing agent. So let's go to Roman E. We are told write the cell notation for the above cell. So how are we going to write cell notation? When you're writing cell notation, we start on the left hand side of the electrochemical cell and we start with the rod. This is N solid or N rod. Then we write phase boundary. Then we write solution of N ions aqueous. Then we write the salt bridge. Sorry, we have not labeled that. This is the salt bridge. And we can take potassium nitrate as our salt bridge. So we can put the salt bridge there. Then we are going to write solutions containing the substance that undergo reduction, phase boundary. Then we conclude with the rod or the electrode for the least reactive metal or the substance that undergo reduction. That's how we write the cell notation. Then next we are told calculate the EMF of the cell. We are still dealing with that two cells of N and also G. Okay, we can do this calculation in two ways. The first way, remember we know N is the reducing agent. So we can write it is a question. When it is reversed, we are going to reverse it. So this is how it is going to be. Aqueous plus electron. Then remember the standard electrode potential also changes and it becomes positive 2.92 volts. Then the side for G, it remains the same. We are not going to reverse it. Then plus E, then we are having G solid. Then the standard electrode potential value here will be still the way it was, which is positive 0.80 volts. So we are going to combine these two half ionic equations. So remember, we don't want this side, we want only to add the standard electrode potential values. So when we add, we are going to get positive 3.72 volts. That's one way that we can do. Or we can do alternatively, we can use our formula. Standard electrode potential value of a cell is obtained by E reduction. E reduction means E oxidation. Okay. The substance that undergo reduction is the one that's the oxidizing agent, which was the most positive 0.80 minus. Then E oxidation is the reducing agent, that's the one that's the most negative 2.92. So when we add these values, we are going to get still positive 3.72 volts. So that's how we are going to calculate the EMF of the cell using these two methods. Next, we are going to proceed to part G or Roman G, where we are told explain whether the reaction represented below can take place. So we have to go back and see what we had in the half cells. Remember, this is solid. Sorry, it's not the gas. The state for that is solid. So we are told to confirm or to predict or explain whether the reaction represented below can take place. So we're having 2 of sodium, N ion aqueous plus M solid arrow. We are told 2 of N solid plus M2 plus aqueous. So let's check. First of all, we can do this in 2 ways. One, we want to check which one is the reducing agent. We start with that. So the first one is N, which is iron. So here N, it's the reducing agent. So that means this reaction obviously will not take place because the reducing agent cannot be displaced from a solution of this ion. So obviously, when we calculate, we are going to get a negative electrode potential value. Okay, we start with that. We are going to say if N is the oxidizing agent here, M is the reducing agent. So what is M? Let's check M. M here is negative 0.44 volts. So we're going to say standard electrode potential value of a cell. We want to use, it will be equal to E reduction minus E oxidation. So this will be equal to, so E reduction will be the side for sodium ion because it's the one that will be the oxidizing agent because of the positive. So here we are going to say negative 2.92 volts minus. Then E oxidation will be the one that's M, and it is standard potential value is negative 0.44. So we are going to say minus 0.44. So when we put this, what are we going to get? We are going to get negative 2.48 volts. So what are we going to conclude if we have gotten that? So we are going to say therefore this reaction cannot take place. This reaction cannot take place. And the reason is this is due to the negative EMF value. Full stop. That's how we are going to answer in part G of our question. So we got to Roman H. We are told which element is likely to be hydrogen. Then we are told give a reason for your answer. So we go and see the half cells given. We check the one that's having an standard potential value of 0.00 volts, and that's K. So we are going to say we are talking about element K. Reason, it has an electrode potential value, of 0.00 volts. That will be the reason. Okay, we got to I. We are told which of the metals cannot be displaced from the solution of this salt by any other metals in the table below. And we are told to give a reason for answer. So they mean which one is the most reducing agent or the strongest reducing agent. That means the one that's the most negative. So our answer is N. So we're going to say N. So what will be the reason? We can give several reasons. One, we can say it is the most reducing agent. That's number one. Number two, we can say it has the least tendency to gain electrons. Number three, or the third reason, we can say it has the most tendency or the highest tendency to lose electrons. So we can pick any. So I can say it is the most reducing agent. it is the most or the strongest, whatsoever we say, the strongest or the most reducing agent. So, or we can say it is or it has the highest tendency of accepting electrons, of donating electrons, of losing electrons. Or we can say it has the least tendency of gaining electrons. So all of these reasons are correct. So we go next. We are told to explain why a solution containing J ions cannot be stored in a container made of M. So we have to check J and also M, that we see whether the two can react. So we are going to see J is having positive 0.52, then the other one that they told us is M. So M is having negative 0.44. So that means M is more reactive than J, so that means it cannot be stored because the two can react, so the container will be dissolving. So we are going to write. So the first step, what we can do is we can calculate first of all whether a reaction can occur or not. So we will start with first of all the formula. Standard electrode potential value of a cell will be obtained E reduction minus E oxidation. So the one that undergo reduction will be the one that's having the ion, and that's J plus. So what will be the standard electrode potential of the J plus? So it's positive 0.52 volts. So we say minus. Then E oxidation will be the one that's having M, and M there has a standard potential value of negative 0.44 volts. So we're going to say negative 0.44 volts. So when we add this, we are going to get positive 0.92 volts. 92 volts. 0.96 volts. So what does this tell us? It tells us that a reaction will occur. So therefore, we are going to say therefore, we can say the overall EMF of the cell is positive. Hence, M will displace J ions. Hence, the container will dissolve. That will be the conclusion that we can give out. So we go to K. So in Roman K, we are told select two half cells that when combined gives the lowest EMF. So when we check, here we're having J and here we're having G. So these two, when combined, they will be giving us the lowest electrode potentials or the lowest EMF. So we're going to say the half cells there will be J ion aqueous plus electron giving us J solid. The other one there will be G ion aqueous plus electron will give us G solid. So in Roman K, we are told calculate the EMF of the cell selected in K above. So we have to first of all write our formula. So we can have the formula to be the EMF of a cell will be equal to E reduction minus E oxidation. So when we check The one for J and the one for G, here we're having G to be the one that undergo oxidation, and that's positive 0.80 minus in bracket positive. The one that's having J is positive 0.52, 0.52. So if we put these values in the calculator, we are going to get positive 0.28 volts as our EMF of the cell. So that will be the end of our video today. Thank you.